Hello everyone, welcome to this video. In this video, we'll be learning what is an automorphism. So we have already studied about isomorphism. So what is an isomorphism? If we define some map phi from some group G1 to some group G2, then this mapping is called an isomorphism between the two groups G1 and G2 whenever the two groups are 1 to 1, whenever they are on to, and this mapping phi is 1 onto an operation preserving in nature, right? This thing we already know, right? And in that case we say the group G1 to be isomorphic to the group G2. That means in properties they are just the same. Now if we in this case, if the group G1 and G2 both are the same group, that means if we define this mapping from the same group to the same group such that this mapping is 1 this mapping is onto, and this mapping is operation preserving, then we call that isomorphism as an automorphism. So this is the definition, and moreover we use the notation AUT of G where we have some mapping from the group G to the group G, right? So this this denote the set of all the isomorphisms which could be defined onto the group G. So that means this automorphism of G would be a set which consists of all mappings such that those mappings, what are they? They are automorphisms, correct? They are automorphisms. Okay. So let's move on to seeing the example. For the first example, we define the function phi from the group of complex numbers to the group of complex numbers, right? We define this mapping when we input the element a plus iota b into it, which is a complex number. The resultant we get its conjugate. So we have a minus iota b here. So this mapping is an automorphism of the group of complex number under the operation of addition. Why is it so? You can check that this mapping is 1 to 1. This mapping is also onto. This mapping is operation preserving, and we are defining it from the same group of complex numbers to the group of complex numbers. Correct? So this forms an automorphism. As for the next example, we have the same mapping, but when we restrict this mapping onto the set of onto the group of non-zero complex numbers, right? So in this case we are excluding 0 from the complex numbers, and the mapping is again the same. Phi of a plus iota b is a minus iota b. However, the operation here was addition, and here the operation that we are considering is multiplication because we have eliminated 0 from it. Now this under the operation of multiplication forms an automorphism, right? So in this case also, this is 1 this is onto, this is operation preserving. For operation preserving we have to prove a dot b is equal to phi of a into phi of b, and in this case for operation preserving we would prove that phi of a plus b is equal to phi of a plus phi of b, right? So both of them, they form automorphisms. As for the next example, if we have R square as the set of all the duplets, so that means we have a point of this kind where the first entry is a real number, second entry is also a real number. So all of the elements, all of the points of the real plane xy, right? So then we define the mapping like this. If we input the point AB into it, we would have the reverse point, which is B comma A. So this is also an automorphism of the group R square under component wise addition. The operation is component wise addition. So here what actually happening by this mapping phi, when we input the point AB, suppose AB point is here. So after applying phi onto it, we will receive a point B comma A. So you see this point has a reflection onto this line y is equal to x, such that we have the same we have a different point b comma a at a same distance from it, right, in a similar fashion. So therefore geometrically the mapping phi here, it reflects each point in the plane across the line y is equal to x. So this mapping phi forms an automorphism, and moreover any reflection across a line which passes through the origin, that also forms an automorphism. In this case, we are particularly taking this line y is equal to x, and therefore the map is simply reversing the numbers in this duplet, right? However, we may take any line which passed through origin, so reflection across that line forms an automorphism again of this plane R square. Again, we have another example which states that if we have any rotation of the plane about origin, so if we rotate whole of this plane either anti-clockwise or clockwise, keeping the origin as fixed, right, about origin, so what would happen? We would again have an automorphism of this plane from onto itself, right? So this is about automorphism. So I hope you understood this definition of automorphism. Well, that is it for this video. Thank you for watching.